All right, so we've been doing a lot of things with models, testing coefficients, looking for differences across groups, etc. But why are we building models? What is it that we build the models for? Normally, it's one of two things. Either we build a model in order to just make predictions, and that's all we care. And the other option is we build a model in order to have a better understanding of certain reality, something that allows us to comprehend what is it that we're studying in the first place. If all we care is just the predictions, then in principle, we should just use as many features as we have, as many predictors as we can have, because in principle, that's going to lead to a better model. Maybe just by a tiny little fraction, but it should be a better model. So in principle, use all the predictions. And how do we measure the model performance? What is the model doing? Well, we could just look into out-of-sample metrics. So we could get a test data set and compute something like RMSE on the test set. That would be our way of quantifying how good the model is, just for the purpose of making predictions. And we don't care how complex the model is. We don't care about what kind of transformations, what kind of variables there are. All we care is, does it make accurate predictions, yes or no? But if what we want to build the model for is to get a better understanding of reality, then we have to go through certain compromises. We could go for a very simple model that allows us to reason about the coefficients, about the relationships, but it might be a poor description of reality. Or we might go for a very complex model that is going to be very difficult to reason about. And so usually it's somewhere in between where we have to hit the sweet spot. And so fitting a good model is actually an iterative process. It's not just a one-time thing. It's something that we should iterate for. And the question is, what predictors do we start with? How many variables do we include in the model, and which variables? Well, first of all, we have to consider domain knowledge. If we have a certain understanding of the problem we're dealing with, and we know that a certain factor is definitely related to the response, or should be, then we should include that in the model. Or if we know by theory that certain things are related to each other, we should include them in the model. Even if it looks like they are not in our data, we should include them in the model. We could talk about pre-specified hypotheses, so we are using the models to test something specific. So of course, the variables pertaining to that specific hypothesis should be in the model. If we are doing some exploratory data analysis and we see possible relationships, then we could just include those variables into the model to precisely test for those hypotheses. We could just run an ANOVA model with all predictors and start with the ones that appear to have the largest impact on the response, the ones with the largest sum of squares, because those are in principle ones that are going to allow us to explain where that variation is coming from. And of course, don't forget about plausible interactions between all these factors. It's not just about including all these different factors, it's about the possible interactions between them, if they are plausible or not. And so we are dealing with the problem of model selection. Out of all the possible models that we could build with a given data set and a given set of predictors, how do we choose? How do we start choosing? So again, what is the best combination of factors? Well, ideally, we could just build all possible models with all those factors, all possible combinations of factors, and then just according to a certain criterion like RMSE or R-squared, things like that, choose the one that is the best. But of course, this becomes impossible once the number of predictors, in this case we call it P, once the number of predictors is large, this problem is unfeasible, or this solution is unfeasible. We cannot just build all possible models with all possible combinations, interactions, etc. Those are too many, way too many to even consider. So we need something simpler. And we're going to talk about two procedures. One is called forward selection and another one is called backward selection. These are the ones that have been traditionally used, although we will criticize them a little bit later. So forward selection, what is it about? Well, the idea is that we start just with the null model. It's the one that only contains the intercept. So we start just by saying the response is the intercept, which models the average, and that's it. There's always a certain amount of error, and the error in this case is going to be very large because we're not even attempting to explain where the response or what are the variables that affect the response. So in principle, we start with something very simple. That's it. And then we start iterating. What do? First, we get all the p-separate two-model coefficients, And we create them by adding to the intercept just one coefficient at a time. So we do beta 0 plus beta 1x1, and we also do beta 0 plus beta 1x2. This is a different model. We fit two separate models. And we do this for all the possible predictors, in this case, up to xp. So we build all the models with only one predictor. And therefore, those are the models with the intercept beta 0 and whatever coefficient is fitted for that one predictor. Out of all these P models, we choose one according to some criterion. For example, which is the one that yields the highest R square. So among all those models, we choose one. Let's say in our case that it's the one including the predictor x2. So now this is our model for now. And then we continue. Based on this model with predictor x2, we start building all the models with two predictors by keeping x2 and adding one of the other predictors that we have left. So now we're going to fit p minus 1 models, of course, because we only have p minus 1 left predictors, and we build the models. So we have, for instance, the one with the intercept, beta 1 x2, this is what we had earlier, and we include now x1. We fit a separate model in which we still have x2, but now we include x3. And we build another model in which we still have x2, but now we include xp, etc., etc., etc. And we do the same. Looking at all those models, we pick the one with the highest R square, because that's in principle the best model with only two predictors. Say in this case that we choose the model with predictor x4. And then we continue. We fit all the models with three predictors, two of them being x2 and x4, and we choose the one with the highest R square. And we continue until we reach a stop condition. And that is when, for example, all the additional variables we include in the model have a high p-value, or when the increase in the R square is negligible. So there's a certain stop criterion that could be something like that. At that point, we stop. And whatever model we are left with, that's our selection. That's the model we select. So we build this model iteratively by adding what in principle seems to be the best predictor at the time. This is forward selection. We go adding and adding more predictors. We could also do it the other way around. We could do backward selection. And what we do is start with the maximal model. What we call the maximal model is the one in which we have all p predictors. So we have the intercept, then x1, x2, x3, x4, etc., all the way up to xp. And by the way, when I say predictor here, it means every term you might include in the model. If you might consider interactions, then the interaction is just one more of the predictors. So all the possible model terms that you might consider as plausible for this case. And then what do? Then we have to identify the predictor, let's call it x minus or x negative, the one with the smallest negligible contribution. So for example, we look into p-values and we choose the one of all those predictors with a non-significant p-value. We choose the one with the largest p-value. That's in principle the one of which we are more certain that the corresponding coefficient is equal 0, or we have more evidence to say that it's not different from 0. And so let's say that in this case, x2 is associated with the largest p-value. What do? We just remove it from the model. What the p-value is telling us is we don't have evidence to support the hypothesis that the coefficient is different from 0. So we just remove it. We are not certain that it's even different from 0, so we just remove it from the model. And then we are left with a model of p minus 1 predictors. And we do the same. We remove that predictor x2 from the model, so you see it's not here, and we continue. We choose the predictor that, out of all of these, has the largest non-significant p-value. And iterate again. Out of all these p minus 1 predictors, which is the one with the largest non-significant p-value? We remove it, refit the model again, and this is very important. We're always refitting the model. We don't look at all these p-values from one regression table. We have to refit the model when we take them out of the model. And so we continue doing this until certain condition is met. For example, all the remaining predictors have a significant p-value. So all the predictors that remain in the model, all of them are statistically significant. Then that's it. We finished. That's our selected model. So those are two quite simple alternatives to build a model, to select a model. We either start with something very simple and make it more and more complicated, or we start with the most complicated model and start simplifying it. There are alternatives to backward and forward selection, and we want to look into those alternatives mostly because forward and backward selection have a number of issues. The thing is that the optimal model is not guaranteed to be found because the process is what we call greedy. We make the best decision at any given point without going back and going forward, or without undoing our decisions. So the perfect model, or the optimal model, is not guaranteed to be found by either of these two selection procedures. And more importantly, what happens is that the coefficients that we end up with in the final model, those coefficients are biased away from zero. And so what this means is that we are inflating the R-square, and we're biasing all the p-values towards zero. So it's going to lead us to a model in which the coefficients are more significant than they actually are. They appear to be even more significant than they actually are. And they might fool us into thinking that there are certain relationships when in reality they are not. Again, because we are not aiming for an optimal model, we are aiming for the best decision at any time, not globally. And so there are more advanced methods to select a linear model. I'm not going to cover them, but they're basically divided into two cases. One is what we call regularization, and we have something like loss or ridge regression. And what they try to do is something like make the coefficients approximate zero in cases in which it looks like the coefficient is not relevant, and it's going to make them zero. And that's a kind of a way of automatically selecting coefficients or selecting variables. And the other one is dimensionality reduction. It's about reducing the amount of variables we have in a certain way, so that instead of fitting a model with, 1,000 predictors, we only fit the model with 10 predictors. And there is an automatic way of reducing those 1,000 predictors to only 10. This is something, by the way, that we will cover later in the course when we see PCA. And what other things could we take a look into when, selecting models or simplifying models? But cross-validation. We could always think about how does the model perform in terms of making predictions, for instance, on a validation set. So we train the model with a certain amount of data, and we test the model on another amount of data. How does the model behave? And maybe we see that a model is way too simple or is too complex for our purposes. Of course, we should always include domain knowledge. This is the most important one. If we know that something is expected to affect the response, include it in the model. And there are several other selection criteria. We've talked about p-values and R-squares, but we could also use AIC, BSC, the Kaik information criterion or the Bayesian information criterion. Those are all valid criterion as well to include in these selection procedures. But if there is one thing that we should always do when we fit models is visualize them. Regardless of how we select, we should always look for patterns in the residuals. We should always take a look at the residuals and see how they behave. Are there patterns? Are there a cluster of points? Does it seem like there's something funny going on in the model? So always try and fit the residuals by fitted value. And it should look something like this, like a random cloud of points. The residuals should be random. That's the whole idea. So it should be just a random cloud of points. If they're not, then that suggests something. For example, it might suggest heteroscedasticity. If we have these non-random shapes, it might say, hey, if we plot here the fitted value by the residual, we see that it's kind of increasing. The larger our prediction, then the larger the error of the model, or the variance here in the response. And this is a case of heteroscedasticity. So it might suggest that if we do a log transformation, this might be a better model because it looks like there's something going on with large values. Or it might look something like here on the right. It looks like we have this pattern in the residuals. This might suggest a quadratic term into the model. So if we include it and refit the model and plot the residuals, maybe it looks something more like what it should, something like this. So plotting these residuals by fitted values might suggest transformations. And of course, it might be something like this, where we see like there's 3 clusters of points, right? Well, this probably suggests that we're missing a categorical variable, a categorical predictor, something that is going to be responsible for the differences between these 3 groups. And really what we're missing here is this categorical predictor telling us differences across groups. So always, regardless of how you select the model, always plot residuals by fitted value. It should really look like a random cloud of points, something like in here. If it doesn't, then probably we need to change the model in a certain specific way through transformations, quadratic terms, which is another transformation, or additional variables that we're missing.